Hello together. We're currently playing around with some Banach spaces, and we have started computing some of their dual spaces, in particular asking ourselves if a given Banach space is reflexive. The first example was just of this type. We were playing around with L1 and L infinity with their typical norms and figuring out, well, dual space of one is isomorphic to the other one, but neither of them is actually reflexive. Doing such an example for the first time, this might seem quite technical, and for this reason I will discuss now two more, where you see more or less the same logic applied in a different variation, but the overall methodology is exactly the same. Right? The first one here, these two spaces, x z0n, so those are sequences that converge to 0 in the supremum's norm, and y again L1, then we will show that the dual space of x is isomorphic to y, but again neither of them is reflexive. We already know that L1 is not reflexive, so we only have to show that x is not reflexive. How to do this? Well, very much like previously in the previous example, we will construct that isomorphism between, actually in this case we also go from this guy to the dual space of this one, so we will construct this map T explicitly. And to this end, we start by, well, picking an L1 sequence. This was already on the slides last time, so I'll just explain it one more time. You start with summable sequence, and then you define linear functional on Z0 in this way here. Remember, I said this is kind of inspired by how the inner product looks like on small L2, but this is not an inner product, okay? Now, a few things to check up front. It is well defined. It is linear functional. That's easy. It is also bounded. The boundedness you get immediately by Hölder inequality. You find out this guy. And now the next step, the idea is to improve this to an equality, because once you have this, then actually the map T, which is defined exactly in the same way as it was in the last example, will be in isometry. So you get the injectivity already for free. Once you have injectivity, then you prove surjectivity, meaning any linear functional on Z0n is of this form yellow star, and then you're done, right? So that'll be the logic. To prove first here that we have equality in the yellow box, in the previous example it was sufficient to look at those E sub n's, those basis vectors. Now here this doesn't work out. You can think about why it doesn't work out. It's easy to see. Instead we work with what I call D sub n, right? So these are truncated sequences in the sense that only finitely many terms are non-zero. So this is clearly an element of some, of z sub 0n, because it converges to 0. And then for some reason there's this peculiar structure up here. You look at these ratios of a complex modulus yk over yk itself, if yk is different from 0, and otherwise you put it equal to 0. It will become clear in a few moments why you have to do this. All right. So first off, we check that the operator norm of dn is equal to 1 in infinity norm for any natural number. And why is this? Well, just look at the definition up there. So these terms where everything is already 0, well, they're not going to compute to your contribute to your supremum, so you only look at the non-zero terms. And the non-zero terms are those guys where you have those ratios, right? Yk in modulus divided by yk. Yeah, but now you have to optimize these in a complex modulus, and then that ratio is going to be precisely 1. Right? So then, of course, that is bigger than 0, so your supremum is equal to 1. That's why that statement is true. Moreover, we find, now this is more important than figuring out that the infinity norm of those dn's is equal to y, we find for the operator norm, so this is here the supremum over all vectors of distance 1 away in infinity norm, fy of x. Remember, this is the infinity norm because you have a linear functional on c sub 0, and that guy is equipped with the infinity norm here in this class. All right. Now this is going to be at least as big as lower bound fy dn, and now you will understand why the dn's are chosen in such a fashion. Okay. So first off, you plug in the definition here. So you have k1 infinity dnk, and then yk, gotta be careful, there's a complex modulus all around, right? Because you got complex modulus. But now you use the definition of dnk, right? So you're gonna, in the next equality, I have to write it on the next page, you're gonna substitute that information in. First off, that infinite series, it truncates, it's a finite sum, because once k exceeds n, everything is 0. So we have first off that this is a finite sum, k from 1 up to n, dnk yk. Again, let's carry around that complex modulus. And now, by definition of the dnk's, well, if the yk's are equal to 0, they're not going to contribute to that sum at all, so I don't make an error there. And if they're non-zero, they're going to precisely divide out that lonesome yk there. And what I have at the end of the day is not dnk, but yk in complex modulus, right, by definition. And now you see I actually don't need that complex modulus all along, so I could have erased it here, here, and all the way through, right, because that thing is already a sum of non-negative terms, so you don't need complex modulus there. Okay, good. And of course this guy, as n tends to infinity, it converges to the one norm of y, which is finite because our element y that we picked in the very first line of this example is a summable sequence. Okay, very nice. Thus all together, and so together, remember the left hand side of this little computation was independent of n. So we have actually that the norm of the operator norm of fy is equal to the one norm of y itself, meaning this t defines in exactly the same fashion as in the previous example. Well, it acts now between different spaces, but that aside, the rule of assignment is exactly the same. That is to say, you assign to the vector y, here in L1, in the previous example it was in L infinity, you assign linear functional on Z0, which is precisely this f sub n, all right, is a bounded linear isometry, right, because we have the equality of norms, all right. Now, so we have injectivity, and now we will show that, well, actually all linear functionals on Z0n arise in this fashion. All right, so in order, and the argument will be kind of similar as we did in the previous example. In order to see that all continuous or bounded linear, that's the same thing here, continuous linear functionals on Z0n arise like, well, the yellow star. What was the yellow star? Well, this was the very first definition here in this example. This was this guy here, right? So I will show that any linear functional on Z0n is equal to some f sub y for y in L1, right? Because that gives you surjectivity of t, and then you will have your isomorphism, all right? So in order to show this, we argue as follows. Well, again, pick an arbitrary linear functional, and now we'll pull the same trick out of our head that we did earlier, but it needs a little bit more work in the current example. So arbitrary linear functional, we take our now those basis vectors en, and we evaluate that arbitrary linear functional on those guys. Remember, the ENs, those are also elements in C sub 0 because they have only one non-zero term, right? So clearly that's a sequence that converges to 0 there. All right, so now you have this. But now you need to do some more work, because in the previous example, we had to convince ourselves that the sequence formed out of all those f sub n's is a bounded sequence, right? And that is super easy. You just use the standard inequality here for the right hand side. It is bounded by something n independent, which is the operator norm of f, right? And then you clearly have a bounded sequence. But now you can't do this anymore, because you have to show in your construction that the sequence that you construct is summable, right, in L1. There's no L infinity here on the left. So then that easy trick doesn't work, so you have to work a little bit harder, all right? So how to do this? Consider xn, Okay, this will be a linear combination of my basis elements ek. Well, maybe I shouldn't use the term basis, because here this Z0 is not a Hilbert space, so yeah, I don't want to use that, so we just use those EKs. Now, notice here, by the way, in this sum, these are the scalars, and these guys here are the vectors, the E sub kn. So that whole thing is a linear combination of vectors in C0n, since that's the subspace. That is going to be a vector in Z0n, all right? And here by default, of course, one of those f sub k's might be 0, but if that happens, you just omit it from the sum, by definition. Omitting those terms from the sum for which f sub k is equal to 0. All right, now, clearly, another clearly, so clearly the infinity norm of xn is equal to 1 for all n in n. Why is this? Well, you just have to remember how the E sub k's were defined. So those are sequences where only the kth entry is 1 and everything else is equal to 0. That's why I say, basis vector, because they're very much like the Euclidean basis vectors. So, in other words, this guy here, how does it look like? Well, it's a sequence. So it has only finitely many non-zero terms. It truncates at n. But how do the first few terms look like? Well, if the f1 is different from 0, then that's going to be your first entry and nothing else, because that guy comes with E sub 1. And E sub 1 has only one non-zero entry in the first component, right? And then the second one, again, if f sub 2 is different from 0, it's going to be like this, and then, well, the last one, provided it is non-zero, will be this, and then everything after that is equal to, well, 0. Let's draw a few more zeros, right? That's how these guys look like. Yeah, but now if you take the infinity norm of this, then you have to put complex moduli around each entry. If the entry is 0, that's just going to be 0, but for all the other ones, that's going to be 1, right? So that's why clearly x sub n is identically equal to 1 in infinity norm. That's why, right? For all natural numbers. And since other computation, so linearity, you hit that sum up there with f, you stick it into f, then f is linear, so then f just sits on the ek, but fek is precisely f sub k as written up there, so you project out that term, and what you have is k from 1 to n f of k, because the denominator cancels out. Remember, only the non-zero terms contribute. Okay, so you have this, and then moreover we also have, well, this guy, but by itself it's useless, which is this one, which is equal to f, because the operator norm here is equal to 1. Not the operator norm, just the infinity norm of x sub n. Alright, so you have this combined together, and since we have together, well, k1n, so you combine the equality with the inequality, so this would be equal to, well, fxn, but since the left-hand side is a sum of non-negative real numbers, you can artificially put here a complex modulus around, and then you use the inequality. So this is less than or equal to the operator norm of f. And this holds true for any finite n, hence the sequence of the f sub k's is summable, right? It's kind of like a Bessel inequality. So for all n in n. Okay, so k1 infinity fk less than infinity, meaning the fn's put together in a sequence form a summable sequence. That is the one step that you have to do here additionally compared to the previous example. And thus f of x, which we look at k1 infinity xk fk. So since this here is summable, and if the xk's are a sequence that converges to 0, this will be a well-defined linear functional on Z0n, right? And thus is a well-defined is a well-defined linear functional on Z0n. Okay, however, now comes the same checking that we did in the previous example. If you evaluate it on En, well, then it projects precisely out the nth f sub n, but by definition this is Fen. So capital F and small f, remember small f was the arbitrarily chosen linear functional on Z0, and capital F is the one that we construct here. They match on all finite, so capital F and small f match or agree on all finite linear combinations of the En, right? Yeah, but those are dense. That's the reason why C sub 0n in the infinity norm is separable. This will be an exercise. And since such linear combinations are dense in Z0n, C exercises, we can conclude by continuity of capital F, or just by continuity of both of those guys, by continuity that capital F and small f agree on all of Z0n. Okay? In turn, remember capital F clearly is in the range of T. In turn, T is surjective. Also surjective. Also surjective. Also surjective, and thus, as in the previous example, its inverse is a bounded linear transformation, right? Remember, so bijectivity by itself does not imply invertibility in this module. This was discussed here actually in the videos. But here we are better. We're not just having bijectivity of T, we have also that T is an isometry. And when you have that, I said it before, then automatically your inverse is going to be bounded. Okay? So then you have this, right? This is bounded linear transformation, meaning, implying that the dual space of X and Y are isomorphic. Okay, so that is done. Now about the reflexivity, we don't have to do much more about this. Finally, by the last example, Y is reflexive, not reflexive. It's not reflexive. Is not reflexive. Not reflexive. So anything isomorphic to it is also not going to be reflexive. This was one of the propositions before we started those examples. So y x star is not reflexive. And if the dual space of a Banach space is not reflexive, then the space itself is not going to be reflexive. This was a theorem right before we started doing the examples. So x star is not reflexive, and hence neither x. Okay, and that's it. So this the reflexivity, we already did all the work in the previous example and in the preparations leading up to the example. Okay, good. So now last example about dual spaces here, at least for the moment, and reflexivity is going to be this one. I already announced it at the end of the last video. So we're going to look now at the LP spaces where P is different from 1 and different from infinity, because these two we covered in the last two examples. And there, now if you're away from P equals 1 and P equals infinity, things work out nicely in the sense that, first off, the dual space of little LP, if P is different from 1 and infinity, is a little LQ, isomorphic is isomorphic to LQ, and P and Q are related by, well, that relation that you remember from Hölder's inequality. Okay. Moreover, both of these guys are actually reflexive Banach spaces. Okay. Comment up front, of course, now that P and Q are both away from 1 and infinity, there's now a perfect symmetry in this game, right? So I can show that the dual space of LP is isomorphic to LQ, but then of course I can just relabel P and Q and get the same statement for LQ, right? So that there's a perfect symmetry here. That's why it's not so surprising that if I manage to show that one of these two guys is reflexive, that the other one will also turn out to be reflexive, right? Because I could have changed the label from the get-go. Okay. So let's do this. The philosophy is upfront very similar to what we did in the past two examples. And we start as follows. All right, so for any y in, let's write it out, y is yn in LP. No, I start with q. Oh yeah, okay, I go again the other way. Okay, this is my choice here. I go from here into the dual space of LP. Fine, could have gone the other way around as well because of the symmetry. But my notes go this way. So LQN, the map f of y, which will be linear function on LP. The map given by f sub y x, which is the same thing again, xn, yn, defines a bounded linear functional on LP. You check this as before, Hölder inequality. Linearity again is clear, boundedness is Hölder inequality, and you have immediately an upper bound for the operator norm because it cannot exceed the Q norm of y. Okay, having that, now we establish equality. Hence, let's write the t now out. In the last example, I defined the t much later, but okay, this is just a way of presenting the things. So if I define t from LQ to the dual space of LP, well, by assigning a vector to that linear functional, then this is a bounded linear transformation whose operator norm cannot exceed 1. This is a consequence of the operator norm of f sub y being not bigger than the Q norm of y. And even better, now comes the standard trick. You want to achieve equality there. Here is the object to look at. In the first example it was En, the second example it was Dn. Now here I call it Gn. So Gn yn bar, yn q minus 2. That exponent there, q minus 2, could be negative, so you have to be careful. You might be dividing by 0, but easy way out is, well, just take the thing equal to 0 if the yn is 0. Then what do we find? The p norm of G is finite. Why is this? Well, again, so if the yn is equal to 0, then the gn will be equal to 0, so you're not going to gain or lose any information there, so you can only focus on the non-zero guys. And then what you will have here, you will have yn bar to the power p in complex modulus, and then yn to the power p q minus 2 in complex modulus. Then, okay, the complex modulus of complex number or its complex conjugate is the same, so you can erase that thing there. And what you have is yn p to the power q minus 1. And now you use the relation 1 over p plus 1 over q is equal to 1. And you can easily convince yourself that that exponent there, p times q minus 1, is just equal to q. So what you have here is the q norm of y raised to the power q, right? Because the q norm has a qth root in it, but there's no root, so I have to exponentiate it. Okay, good. And this is finite because our starting object y was a vector in LQ, right? Good. So we have this. Thus, implicitly assuming that my starting vector is not the 0 vector, because if it's 0, then, well, the linear functional is going to send it to 0, so I'm not going to gain any information from that. So f of y is then, by definition, this is supremum x in x, which is LP, non-zero. That's just the definition of the operator norm. One way to write it down. xp, this is going to be at least as, well, if I evaluate it on my g. Right, so the subscript is y, the argument is g. Might be hard to see. And now what happens here is, well, now I use the definition. The definition of f sub yg, if you substitute it in, well, it's not on this slide, it's on the previous slide, but anyway, so what happens in the bottom, that is on this slide. So here is the p norm raised to the power p, so that's why in the bottom I get y, q, and then q to then to the power q over p, right? Because you have to take into account that root. And the other one, you just use the definition of f sub y. You can convince yourself that that is going to be y q to the power q. Okay, good. So you have this, and now you just do some algebra with the exponents. What comes out here is precisely the q norm of y, right? Because you have that q, oops, in yellow, q times 1 minus 1 over p. This will be your exponent here is equal to 1. Okay, so you have this, and that gives you the isometry as you wanted. Okay, so showing that fy in operator norm is equal to the q norm of y. Okay, now we have to show that it's surjective. This is almost like in the previous example, and then we will convince ourselves that both of these guys are actually reflexive Banach spaces. Okay, I'll see you soon.